All right, 12.5. Last section of chapter 12. Oh. Arc length and curvature. So this is an extension of something that you talked about in Cal 2, specifically with parametrics. You learned how to find the arc length of a curve. Remember, arc length would be like if I were to snip a curve in two places, lift that curve, lay it out flat, measure out how long it is. That's arc length. It's the length from point A to point B if you're moving along a curve. And we can deal with this in both 2 dimensions, 3 dimensions, and more using vector valued functions. Because remember, the whole big idea in chapter 12 is that vector valued functions are pretty much the same thing as parametric equations. Yep, true story. So, with parametric equations, you learn that you can find the arc length by taking an integral, specifically from A to B, start to finish, of the square root of derivative of x squared plus derivative of y squared dt. That should look familiar. That's right, that's the magnitude of a vector, right? So basically, if we take the integral of the magnitude of a vector, we get arc length. And to extend it to 3 dimensions, of course, it's the same idea as with magnitude, right? So all those ideas kind of laid out right here. Let's look at an example. We want to find the arc length of the curve given by r of t, and we're specifically looking for the length between t equals 0 and t equals 2. So for this one, first thing I need is to find my magnitude for r prime, actually. Yep. So not r, just r prime. So we're going to find r prime of t first. All right, derivative of t is 1, so I. Derivative of this, we bring the 3 halves down, right? Then we're going to get 4 over 2 because the 3's will divide. 4 over 2 is also known as 2. So we have 2t to the 1 half. And then if I bring this 2 down, that 1 half will become 1. So plus tk. And I forgot my j here. There we go. So now we have our derivative. So if I want to find the magnitude, all right, we just use our formula for magnitude. Square root of first component squared is 1. Second component squared will be 4t. Third component squared will be t squared. So this is our magnitude. Right, so to find the arc length s, I would need to take the integral from 0 to 2 of the square root of 1 plus 4t plus t squared with respect to t. Now, if you were to try to factor this, you wouldn't be particularly successful. No. So instead, I would say that this is not something that is integrable just by elementary methods. In fact, in the textbook, when they do this example, they call on an integral table to get the antiderivative. Um, with that said, though, I am going to just evaluate this using Desmos calculator. Right, and again, this is not something that you would be expected to anti-differentiate from scratch. However, any of the methods that you learned in Cal 1 and Cal 2 would be fair game. Um, so let's see, typing slowly. All right. We end up getting that this is about 4.816 around to 3 decimal places. So that's the setup. Find your magnitude, take the integral of your magnitude from point A to point B, and la-di-da. Let's look at another example. So this one doesn't explicitly give us the values of t. We have to use our brain space to figure some stuff out. So we want to find the length of one turn of the helix given by this. So we know that a helix moves kind of in this circular pattern that goes up. So in 3 dimensions, it kind of looks like a spring in a way, right? So one turn of the helix is going to depend entirely on these trigonometric terms. So think about it, what range of t would we have to use to go completely around the unit circle once? 0 to 2 pi. Yep. And that'll work for this one because neither of these t's have a coefficient. If they did, then we would have to multiply 2 pi by that coefficient. Well, actually divide 2 pi by that coefficient to figure out how far we need to go, right? So one turn of the helix is going to be from 0 to 2 pi. So now we have the bounds for our integral. We do, however, still need to go and find r prime and the magnitude of that. So r prime, derivative of b cosine t, we get negative b sine of t, I. Derivative of b sine t, we get b cosine t, j. And then derivative of this thing, t, would just be that thing. It's a constant. It's like if you have a number t, and that's the k component. Now that we have r prime, we can get the magnitude of r prime, just as we have before. So b, negative b sine t, when I square that, I get b squared sine squared t. B cosine t, when I square that, I get b squared cosine squared t. And this is a square root, so when I square that, I get 1 minus b squared, the thing that is under the root. And we know this trick. We've seen this song and dance several times at this point. We know that this whole thing is going to just be b squared. Okay. Because we can factor b squared out, that leaves behind sine squared plus cosine squared, which, as we know, is equal to 1. So this is b squared times 1, which is b squared. So now if I simplify even further, I see that these two terms will subtract out, and we're left with 1. So the magnitude of r prime is 1. Look at that. It's a unit vector. Pretty fun. That actually makes the integration super easy because now we're just taking the integral. So our arc length S is the integral from 0 to 2 pi of 1 dt, which is 2 pi. 2 pi minus 0, 2 pi. All right, next one, we want to find the arc length function. So this time when we get our arc length, it's going to be a function of t, the parameter, or the line segment, not ling segment, given by this vector valued function for t between 0 and 1. Then we want to write r as a function of the parameter s. Okay, so this is a skill that we're actually going to use a little bit in some of the later examples involving arc length and the other thing we're going to talk about, curvature. So starting off, we'll get r prime. So r prime, derivative of 3 minus 3t is just negative 3. That's the I component. And then derivative of 4t is 4, so plus 4j. So the magnitude then of r prime is going to be the square root of negative 3 squared 9 plus 4 squared 16, which is equal to 5. Oh, Pythagorean triple. Look at that. All right, so we've got the magnitude is 5. That's literally it. Now, if I want to get my arc length as a function of my parameter t, um, yeah, I essentially need to take my starting value of t, which in this case is 0, and I'm not going to go up to 1. I'm going to go up to t. 5. I don't like that notation. All right, t prime. Why not? Okay. So then the antiderivative of this, we get 5t prime from t prime equals 0 to t. And we get our answer 5t. So s is equal to 5t. Now, if I wanted to rewrite r, my original line segment, in terms of s, one approach I could take is to solve this equation for t. So I could do that by just dividing both sides by 5, right? And anywhere that I see a t in r of t, I can replace it with s over 5. So we would get r of s is equal to 3 minus 3/5 s I plus 4/5 s j. So you see, all I had to do there is solve for t, and then anywhere that I saw a t in the original, I replaced it with s over 5. And now we have the original function written as a function of arc length instead of just some random parameter. So now that we've looked at a couple examples of arc length, we can talk about the other thing, curvature. So curvature is essentially how sharp a turn is. So if I'm driving in the mountains and I'm going around switchback, like it goes the other way, right? This might have some curvature to it, but when we get to the point where we're switching direction, that's where the curvature is the highest. So it's just a number that describes how sharp a turn is. Um, One thing that people typically talk about when they learn about curvature is circles. Because if you think about it, a circle is basically the same amount of sharpness the entire way around, right? In other words, the curvature of a circle is constant. In fact, it's related directly to the radius of the circle. Because a circle that is super, super big isn't going to have as much curvature as a really small circle, right? Think about if you're doing donuts in a parking lot, right? If you want to make a smaller donut, you got to turn your wheel more. Don't make donuts in parking lots. It's bad for your tires. Anyway, so first thing, we can actually figure out the curvature in a couple of different ways, similar to how we had all those different formulas for the other things. And I don't want you to worry about memorizing all of these either, right? I will provide some formulas so that you can focus on concept and being able to know which one to use. With that said, if we have our unit tangent vector written as a function of arc length, kind of like how we did in the last example, then we can find the curvature by just taking the magnitude of t prime. Again, though, this has to be written in a way that our parameter is the arc length. Otherwise, this definition kind of falls apart. Luckily, you don't actually have to do that a lot of the time because there's a relationship between arc length and our unit tangent vector. It involves the radius, or not the radius, the r prime, the derivative. All right, so one way that you can find the curvature without having to rewrite in terms of arc length is using this definition here, right? So that's the magnitude of t prime divided by the magnitude of r prime. And side note, which I said here, curvature is represented by the Greek letter kappa, not k. It's kappa, kappa, no cap. All right, so the first example with curvature is to show that the curvature of a circle whose radius is r is k equals 1 over r. So the first thing we'd need to do is write out the equation of a circle as a vector-valued function. Easy enough because of the unit circle, right? Remember with your unit circle, you essentially had x is equal to cosine of theta. Technically, x is equal to r cosine theta, radius times cosine of angle, which you also could just write as t instead of theta. Yeah. And then for the y, you had r sine theta, sine t. Yeah. So if I wrote that as a vector valued function, right, to be consistent with the notation, we could use r, but that would be annoying. So we're just going to write, pick a letter, any letter, C, circle. There we go. So our vector valued function C would be r cosine of t I plus r sine of t j. Right, and this is just a circle in a two-dimensional plane with a radius of r. So I would need to get, or so if I wanted to use this definition of curvature, I would need to start by getting my unit tangent vector and its derivative. So we know that to start off with, to get your unit tangent vector, your first step is always to find the derivative. So C prime would be negative r sine t for the I component plus r cosine t for the j component. To get our unit tangent vector, we would have to divide this by the magnitude of C prime. So we're going to need it anyway for that definition of curvature. So the magnitude of C prime, we get the square root of, square this guy, you get r squared sine squared t plus r squared cosine squared t. Using our little trick that we know that this is going to end up giving us r. So our unit tangent vector as a function of the parameter t is equal to c prime of t divided by r, which is basically going to give us negative sine of t I plus cosine of t j, right? Because when I divide by r, the r's will divide out. Okay, so now that we have our unit tangent vector, we need to get t prime as a function of t, which will be simple enough. That's negative cosine of t I minus sine of t j. So now that I have t prime, we can get its magnitude, which we're going to need for the curvature formula. So we have the magnitude, so that's the square root of this squared, which will give me positive cosine squared t, plus this squared, positive sine squared t, which we know is 1. Square root of 1, we get 1. So the curvature kappa, can make it fancy so you know it's Greek. Wow, that's so fancy. All right, is going to be the magnitude of t prime as a function of t divided by the magnitude of c prime of t. Notice I used c instead of r because that's what I named the original function. We knew that this was 1, and we showed that this was r. Therefore, the curvature of a circle with radius r is 1 over r. Pretty fun. Really fun. Okay, now for the next example, we want to find the curvature of this curve given by r of t. So again, we have to figure out our unit tangent. Step 1 for that is finding the derivative r prime. All right, derivative of 2t, we get 2. Derivative of t squared, we get 2t. Derivative of minus 1/3 t cubed, we get minus t squared. And I forgot my j again. There we go. All right, so this is r prime. Remember, to get our unit tangent vector, we're going to need to find the magnitude of r prime. So I have the square root of 2 squared, 4. 2t squared, that's 4t squared, because the 2 also gets squared. And then negative t squared squared gives me positive t to the 4th. You might be thinking, oh no, that's so gross. But you know what? If you know how to factor, it's actually not. All right, because this is going to end up being a perfect square. Specifically, this is going to be t squared plus 2 squared. If I take the square root of that, I just get t squared plus 2. Yep. So all that stuff you learned back in basic algebra can make your life so much easier here. All right, so we have the magnitude of r prime, which we can now use to find the unit tangent vector. So t of t, so t of t is going to be r prime divided by its magnitude. So we have 2 over 2 plus t squared. That's the I component, plus 2t over 2 plus t squared. That's the j component, minus t squared over 2 plus t squared. That's the k component. Now we want to find the magnitude of this unit tangent vector. Actually, no, that's not true. We want to find the derivative of this unit tangent vector first. Okay. And that's going to give us the, what's it called? That's going to require us to use a chain rule, everyone's favorite. So a side note here, and this is going to apply to pretty much all the derivatives that we're going to do. Remember, if I have something like this in the denominator, I can always write it as 2 times 2 plus t squared all to the minus 1. That's an option. Remember, the other option is using the quotient rule, and we have our cool little song for that one, right? F prime g minus f g prime, all of g squared. All right, so yeah, we could do this. The thing is, when we get to these two terms, that would end up giving us both a chain and a product rule. And we can avoid that by using quotient rule. So rather than rewriting, we'll actually just do quotient rule. So derivative of top is 0 minus top times derivative of bottom. So 2 times 2t all over denominator squared. That's the I component. For the j component, derivative of top is 2 minus 2t times derivative of bottom all over bottom squared. That's the j component. And for the k component, we get 2t times the denominator minus t squared times derivative of the bottom all over the bottom squared. And that's our k component. So now we've got our derivative of the unit tangent vector. And from there, we can actually go through and find the magnitude and use this formula for curvature. There's something I want you to think about, though, before we get into doing all that work. How did we find arc length? We took the integral of the magnitude of r. Mhm. What was the magnitude of r? Was t squared plus 2. That's relatively simple for us to integrate. So we could have come up with an expression for s, the arc length. And from that, we could have actually written out our unit tangent vector in terms of arc length rather than getting all messy with this stuff. Fun exercise. I mean, we've already done the work, so I'm going to keep going with what I'm doing. But when I say, like, look at it, figure out what makes sense, that's an approach you can take. So before I do anything else with this, we're going to want to simplify our t prime. So we get negative 4t over this guy squared. Okay, now if I distribute, I'm going to end up getting 4, right? So that's 4 minus 4t squared. Oh, yeah. So we get 4 plus 2t squared minus 4t squared. So this is where we get. And then this one we can also simplify a bit. So we end up getting 4t squared, or 4t from distributing to that first term. Second term, we would end up getting 2t cubed. Thing is, when I multiply this, I also get 2t cubed. So those will end up subtracting out, and we're left with just 4t as the numerator. All right, which ends up matching what we got for the I component. So with that, we've already got our T prime. We already know what the magnitude for R prime is. So we are going to write out the magnitude for T prime and use that to get our curvature. So with T prime, we have the square root of first component squared. So that'll be positive 16 T squared. Negative will become positive. 4 squared is 16. T squared is T squared over 2 plus T squared to the fourth now. And for my J component, we have 4, minus 2T squared squared over 2 plus T squared to the fourth now. And for the K component, we get 16T squared over 2 plus T squared all to the 4. Now, reminder, you can add these because they all have the same denominator. And remember, when you have the square root of a fraction, you can write it as the square root of the top over the square root of the bottom. So essentially, we'll have the square root of these three summed together. So 32t squared, which I got from combining 16 and 16. And 4 minus 2t squared squared, which will expand because it is going to make our lives a little easier, divided by the square root of that to the fourth, which would just be that squared. So doing an expansion here, multiply 4 times 4, you get 16. So let's write it out. 32t squared, 16, minus 8t squared minus another 8t squared gives us minus 16t squared, plus 4t to the 4. So then I have these like terms that I can combine. So I get the square root of 4t to the 4 plus 16t squared, which I got from doing 32 minus 16, plus 16. This is all over 2 plus t squared squared. Now, if I were to factor it, so first off, I know that I can factor a 4 out from all three of these terms. And since we're under a square root, when I factor a 4 out, I can actually pull a 2 out of the square root. Okay. Now, one thing that you'll notice is that this is the exact thing that we factored at the beginning of the problem. So I already know that this is going to factor to t squared plus 2 squared. So when I take the square root, that takes out the squared. If I have this in both the top and the bottom, then I can divide one factor of each. And we end up simplifying to 2 over 2 plus t squared. So that's going to be the magnitude of t prime. So my curvature kappa, make it nice and fancy, it's going to be the magnitude of t prime divided by the magnitude of r prime. So the magnitude of t prime we got was 2 over 2 plus t squared. Since I'm dividing a fraction, I'm going to multiply by the reciprocal of r of t, which we got to be just t squared plus 2, or 2 plus t squared. So we end up getting that our curvature is 2 over 2 plus t squared squared. And that allows me to find my curvature for any value of my parameter t. So if I know t is 0, for instance, my curvature would be 1/2. If t were 1, then my curvature would be 2/9, which is less than 1/2. So it would be like sharp turn, kind of evening out. And that gives us curvature. Now, the last idea that I want to talk about in this chapter is how we can actually use arc length and curvature to do what we did in the last section, decompose the acceleration into tangential and normal components. So, so specifically, we get this formula that the tangential component of our acceleration is the second derivative of the arc length with respect to t. The normal component for our acceleration is given by the curvature multiplied by the first derivative of the arc length with respect to t squared. So we look at this in action. Let's say that we have this curve R that tells us the the path of an object moving in 3 dimensions. We can find the tangential and the normal components of the acceleration by using what we know about curvature and arc length. So to start off with, my first step is to find the derivative. All right, because in order for me to find the arc length, I need to know the magnitude of the derivative. So r prime of t is going to be 2i plus 2tj minus t squared k. The magnitude of r will be the square root of 4 plus 4t squared plus t to the 4. Yeah, look at that. It's the same one from the last problem. So we can actually factor that to t squared plus 2 squared. And when I take the square root, that leaves us with just t squared plus 2. So we've got r, we've got the magnitude of r. Now, if I want to find the arc length as a function of t, remember we're just taking the integral, and here I'll just use a different variable. So from 0 to t of, instead of t, I'll write something else like u. Why not? Just because I don't want my differential and this bound to be the same variable. That's why I did t prime in that last one as well. So when I take the antiderivative, we end up with u to the third over 3 plus 2u. We're evaluating that from u equals 0 to u equals t. So for my arc length, I end up getting t cubed over 3 plus 2t. So this is my arc length. Now, if I want to find my components, as our notes said here, I need to find the second derivative of the arc length. All right. So my tangential component is going to be second derivative of s with respect to t. So if I take the first derivative, I end up back at t squared plus 2. So the second derivative would just be the derivative of this, 2t. So that's my tangential component. If I want to find the normal component, then I need to figure out my curvature kappa. Right, to do that, we would need to know our unit tangent vector as a, yeah, we would need to know our unit tangent vector as a function of arc length. Or we could go through that process where, or we could go through that process where we take the magnitude of t prime divided by r prime, but I don't think anyone wants that heartbreak again. So, yeah. So if I want to find my unit tangent vector, remember that's just each component divided by the magnitude of r. Yeah. Wait, hold on. Oh, y'all, this is literally it's late. So y'all, this is literally the exact same function r that we found the curvature for in the last example. So rather than going through that computation all over again, we're just going to steal the kappa that we got from the last one. So that was 2 over t squared plus 2 squared. Yep. So we got this from the last example. We just pulled it because it's the exact same function, right? So to find my normal component for the acceleration, I just need to take my curvature kappa and multiply it by the first derivative of my arc length, right? And that's squared. So kappa is given by that. My first derivative of arc length, remember, was this guy, t squared plus 2. And we're going to square that. And that is super convenient because it gives us essentially 2. So the normal component of our acceleration is 2. The tangential component is 2t.